Welcome to the Analytical Instrumentation Facility, or AIF, at North Carolina State University. I'm Jacob Jones, Director of the AIF and a Professor of Materials Science and Engineering. The AIF is the largest and most comprehensive open-access materials characterization facility in the southeastern U.S., with several $1 million of instruments dedicated to microscopy, spectroscopy, diffraction, surface science, and chemical analysis. In parallel, we have an expert professional staff who are welcoming, helpful, and enjoy training and educating the user base. I hope you enjoy meeting some of them on your virtual tour today. AIF is a member of the Research Triangle Nanotechnology Network, or RTNN, the National Nanotechnology Coordinated Infrastructure, or NNCI, and is a core facility at NC State. I hope you enjoy your tour, and don't forget to visit us at aif.ncsu.edu.
Hi, my name is Tanzania Ray, and I'm the Business Officer for the Analytical Instrumentation Facility. As the Business Officer, I facilitate the agreement process for all of our external customers. This includes any startup agreements, such as order forms and lab use agreements, as well as modifications. I also ensure that these customer agreements are reflected in our Mendex system. As the Business Officer, I also take care of the accounts receivables for the facility. Another aspect of my role is to manage the rates being charged to all of our facility users, ensuring that they are fair and meet industry standards. If you are looking to become an external user of our facility, please feel free to reach out to me directly to help you get started. Thank you.
Hi, I'm Charlotte Huang. I'm the Associate Director of AIF. I'm also the Associate Professor in Mechanical and Aerospace Engineering at NC State. My primary responsibility at AIF is to expand the biological imaging capability in the facility and also work on some administrative work.
Hi there, my name is Anna Lumpkin and I'm the University Program Specialist here at the Analytical Instrumentation Facility. I help manage our lab management system, Mendex, as well as all of AIF's digital content. I update our website, I send out our monthly newsletter, and I also post to our LinkedIn account and our YouTube channel. If you ever have any questions about the AIF or our capabilities, please feel free to reach out to me.
I'm Wenpei. I'm TM Principal Scientist in the AIF. I also work at Material Science and Engineering Department as an Assistant Professor. Here at AIF, I work with other scientists to develop new imaging techniques. We try to understand material structure and behavior at the atomic scale.
Hello, I'm Roberto Garcia. I'm the Operations Manager and the FIB Lab Manager here at the Analytical Instrumentation Facility. Behind me is the Focused Ion Beam Instrument, or the FIB for short.
The system is equipped with a field emission SCM column and a gallium ion column. The unit also has several detectors, which includes an EBSD detector for orientation imaging and an EDS detector for elemental information. The FIB also has a platinum gas injection needle for deposition and an Autoprobe 200 lift-out needle. The primary use of the FIB is to create samples for the TEM. In this case, a thin 2-micron window of the material is removed and placed onto a TEM grid, where it is then thinned to electron transparency.
Hi, my name is Bibi Qinzhang Zhong. I'm the XRD Lab Manager at Analytical Instrumentation Facility. Behind me, this is a Pananalytical Imperium X-ray diffractometer. This is how it looks like inside the Imperium. On this diffractometer, we install a copper X-ray source, a Bragg tunnel optics setup, a Pixel 1D linear detector. This setup allows very fast data collections. The diffractometer can be operating under two geometries, a refraction geometry and a transmission geometry. We have 5 different sample stages that can be installed on this diffractometer: 1 room temperature spinner stage and 4 non-ambient sample stages. These sample stages allow us to perform the XRD measurements as a function of time and temperatures in a very wide range of non-ambient environments. The operating temperature range we can use on this system is from -190 Celsius to 2300 Celsius. And we can use in different environments in the non-ambient chambers, such as air, vacuum, inert gas, and reactive gas. Besides the phase reactions, we can also use the in-situ XRD measurements to study the phase transition, crystallizations, that is expansion, reduction and oxidation reactions in different materials.
Hi, I'm Aaron Bowell. I'm the bio-EM scientist here at the AIF. Behind me is the Leica ACE 900 freeze fracture system, which we use for both biological and some material science applications.
The Leica ACE 900 operates at high vacuum and is equipped with 2 E-beam sources for platinum and carbon coating replicas. The ACE 900 has several different holders to accommodate a wide range of samples and can generate double replicas as well as knife fractured replicas. Freeze fracture is suitable for examining both biological as well as soft materials and polymers. The Leica EM ICE is used to cryo-immobilize samples in a near-native state using liquid nitrogen and high pressure. Features that are unique to the EM ICE is the ability to perform light and electrical stimulation prior to freezing with millisecond precision. The instrument at the AIF is currently outfitted with light stimulation, but can be retrofitted with electrical stimulation should the need arise. Following high-pressure freezing, samples can then be transferred to the Leica EM AFS-2 for freeze substitution, where the sample is fixed, stained, and embedded for TEM analysis.
Hi, I'm Fred Stevie at the Analytical Instrumentation Facility at NC State University. I'd like to tell you about X-ray photoelectron spectroscopy. This is our SPEX XPS spectrometer. We have multiple sources on this instrument. Most commonly used, the magnesium aluminum dual anode. The X-rays from the source irradiate the sample, and the sample is located inside the analysis chamber. The electrons that are emitted are analyzed through a hemispherical analyzer and then detected. Samples are loaded in an air interlock as shown here. Our pressure in the instrument is typically in the low 10 to the minus 10 millibar range. This image shows a reference spectrum for silicon obtained with the magnesium K-alpha X-ray source. Each element has a unique XPS spectrum. The silicon 2P peak has different binding energies for different chemical states. This next image shows a spectrum obtained with a magnesium source on the surface of a piece of silicon. The native oxide on the silicon appears as silicon and oxygen peaks. The carbon is due to surface contamination.
My name is Chuck Mooney. Behind me is the Analytical Instrumentation Facility's ultra-high resolution scanning electron microscope. It's a Thermo Fisher Microscopes Varios 460L. It's capable of half nanometer resolution in X and Y, from 2 kV to 30 kV. It has 3/4 nanometer resolution at 1 kV and 1 nanometer resolution at 500 eV. The Varios SEM is equipped with an energy dispersive X-ray spectrometer detector, an electron backscatter diffraction detector, It also has a standard complement of an Everhart Thornley secondary electron detector, a through the lens secondary electron detector for ultra-high resolution mode. There is a standard insertable backscatter detector for compositional contrast. The item right here on the side of the column is a oxygen plasma generator for cleaning samples in situ, and the system is also equipped with a load lock so the inside of the microscope stays under vacuum and clean.
Hello, this is Angel, and I'm the lab manager at Analytical Instrumentation Facility at NC State.
ToF-SIMS is a highly sensitive surface analytical technique, typically using a pulsed and focused ion beam to produce secondary ions from outer 1 to 2 nanometer of the materials. The ejected ions are then extracted and measured by their flight time, which is proportional to their mass-to-charge ratio. So in our ToF-SIMS instrument, there is a pulsed bismuth liquid metal ion source, typically used for analysis beam, and a cesium spectrum beam used for depth profile analysis. This vertical tube is the time-of-flight mass analyzer. The mass spectrum collected provides detailed information about the molecular structure of the surfaces. The imaging ToF-SIMS provides a spatial distribution of different species with 300 nanometer lateral resolution, and the depth profile provides elemental distribution from the surface to the bulk with ppm level detection limit and a few nanometer depth resolution. This horrible confocal Raman microscope comes with an integrated laser system with 532 nanometers and 785 nanometer laser wavelength. This microscope combines Raman spectrum and optical microscope, providing sample identification and chemical imaging on a microscopic scale. The Raman hosts a variable temperature stage with a range from negative 196 degrees C to up to 600 degrees C. The JOL GSM 1700F SEM outfitted with a cryogenic transfer system, in situ gold platinum spartocoater, and cold stage, and this can be used to evaluate hydrated samples without the need for drying, making it an ideal imaging tool for volatile or beam-sensitive samples. This SEM is also equipped with a complete catoluminescence solution to analyze CL signals over a wide spectral range from 200 nanometers to 2200 nanometers.
Hello, my name is Christopher Winkler, and I am the TEM lab manager here at the Analytical Instrumentation Facility. I'm sitting in front of one of 3 TEMs that we have in our facility. This is the probe-corrected monochromated Titan. The 4D STEM detector on our Titan allows us to collect a diffraction pattern at every probe position on our sample. We can process these diffraction patterns to look at things like strain, different phases, chemistry, and many other interesting parameters regarding our samples. The 4 EDS detectors on our Titan allow for efficient collection of the X-rays generated from our sample and allows us to do things like atomic resolution EDS mapping. Our Titan is equipped with a monochromator and an energy loss spectrometer with dual EELs and fast shuttering capabilities. This allows us to do high energy resolution energy loss spectrometry.
Hi, my name is Anton Jansson, and I work as a postdoc here at AIF's X-ray computed tomography laboratory that you can see behind me. In X-ray computed tomography, or CT, we illuminate your sample with X-rays, and from that we can extract structural and relative density information. We can scan anything from soft tissues to metals. At AIF, we have 2 different CT systems. The most powerful one behind me can scan samples ranging from microns to several inches, and we can achieve spatial resolutions beneath a micron. The system relies on optical magnification to achieve this, thus it is also known as an X-ray microscope. Let's take a look at an example of what we can do here. The sample is being rotated between the X-ray source on the left and the detector array on the right. Here we can see the resulting 2D radiographs of the sample as it is being rotated. The specific sample was scanned in 3 sections that were later stitched together. We could scan the entire sample at once, but this way we could achieve a higher resolution. These projections are now reconstructed into a 3D volume. Here we can see the final result, a fully interactable 3D volume of our sample. Cutting through the sample, we can see the state of its internals without any real damage to the sample. In the 3D data, it is possible to isolate and measure at will. For example, here particles are isolated for further analysis. Components can also be isolated for analysis, for example the collector. Here, we scroll through a side view of the sample. This way, each slice of the sample can be analyzed individually.
Hi, I'm Maud Kachera. I'm the Associate Director of the Research Triangle Nanotechnology Network, or RTNN. The RTNN is one of 16 sites in the National Nanotechnology Coordinated Infrastructure, which is funded by the National Science Foundation. The RTNN is a partnership between North Carolina State University, the University of North Carolina at Chapel Hill, and Duke University. The RTNN brings together the nanotechnology core facilities at each of these 3 institutions. Throughout the year, the RTNN offers programs that overcome traditional barriers to accessing these types of facilities, such as distance, cost, and awareness. One of our flagship programs is our Kickstarter program. This program provides free access to nanotechnology tools in our facilities to new and non-traditional users, like those from non-R1 institutions or from small businesses. The RTNN also developed a course that is housed on the Coursera platform. This course, called Nanotechnology, a Maker's Course, raises awareness of nanotechnology tools and how to access our facilities. Students first get an overview of a tool or a technique and then see a demonstration of the tool, which helps them to better understand how the tool is used and how they could potentially use it in their own research. The RTNN is also committed to education and outreach in our community. One of our favorite things to do is to bring our portable scanning electron microscope to local schools, museums, and libraries. If this sounds fun to you, I encourage you to apply for our RTNN Student Ambassadors program. Student ambassadors help us at all of these events and make them a success. If you'd like to learn more about the RTNN or any of our programs, please feel free to reach out to me directly. I look forward to hearing from you.
Hello, I'm Philip Streeter. I am a project scientist with the Research Triangle Nanotech Network, which the AIF is a part of. I manage a couple of different labs here at AIF at NC State, including our Nanoindentation tools, the Keyence laser profiler, and I'm also an assistant in the SEM and AFM labs.
This is our Hydrotron TI-980 triboindentor, often simply referred to as our nanoindentor. Nanoindentation involves forcing a rigid probe into a sample to determine that sample's mechanical properties, primarily reduced modulus and hardness. The maximum displacement of the indenter tip is about 5 microns, and thus the testing volume is usually no more than a few thousand nanometers, making it extremely sensitive to the outermost surface of a sample or material. It's a great instrument when you need to determine physical properties of a material when the actual volume of the material is very low, like in the case of thin films, or where your sample is too small for other physical testing modes like microhardness or tensile testing. This instrument is officially considered a tribo-indenter because in addition to the one-dimensional quasi-static nanoindentation, it's also possible to do other tribological analyses, including nanowear and nanoscratch testing, where you can test coefficient of friction and induce film delamination, among many other modes.
Hi, my name is Toby Tung. I work at the Analytical Instrumentation Facility as one of the TEM lab managers. Behind me, you're looking at the control system of our brand new Thermo Fisher Talos F200X. The Talos is incredibly easy to use thanks to the new software package that they've developed called Velox. The Thermo Fisher Talos is an analytical scanning transmission electron microscope powered by a field emission source under high vacuum. It is equipped with a Super X detector, so there are 4 EDS detectors that can obtain the chemical information of your sample. We can also capture images up to 4x4K resolution. Not only can we perform traditional TEM and STEM experiments, we can also perform in situ experiments thanks to Gatan and protochips holders. We can perform cryo, liquid, gas, heated, and 3D tomography experiments with a variety of holders that the AIF has available for TEM.